Welcome to my channel Ravi Kumar Academy. In this lecture, we are going to learn how to solve problems related to eigenvalues and eigenvectors. So, in this lecture, we are going to see all six different types of problems related to eigenvalues and eigenvectors. Like three eigenvalues are different, two eigenvalues are different, all three eigenvalues are same, and three eigenvectors exist. Only two eigenvectors exist, only one eigenvector exists. So this type of problem, all different types of problems we are going to deal in this lecture. So let us take the first type of problem, A equal to, the matrix A equal to 314 026 005. So if you take this one, I'm not writing anything like eigenvalues, finding eigenvalues and eigenvectors here. All problems are related to finding eigenvalues and eigenvectors only. Here, the given matrix is a triangular matrix. What is a triangular matrix? It is either the lower triangle or upper triangle below the principal diagonal or above the principal diagonal. You have all zeros. It is a triangular matrix. So here you have all zeros below the principal diagonal. Therefore, it is upper triangular matrix. And by the properties of eigenvalues, we have discussed in the previous lecture. You can refer to that video also. So from the properties of eigenvalues, the eigenvalues of this matrix are nothing but the principal diagonal elements. What are the principal diagonal elements? 3, 2, 5. So therefore, without finding the characteristic equation directly, you can write the eigenvalues of this matrix, which are nothing but 2, 3, 5. I am writing in the increasing order, 2, 3, 5. So what is the matrix A minus lambda I? The matrix A minus lambda I is here. Just subtract lambda from the principal diagonal elements. 3 minus lambda, 1, 4, 0, 2 minus lambda, 6, 0, 0, 5 minus lambda. So this is the matrix A minus lambda I. So to find the eigenvector corresponding to lambda equal to 2, the first eigenvalue is lambda equal to 2. So what you have to do is, the equation is A minus lambda I into x1 equal to 0. Here, what is x1 or x? X is a vector xyz. Say column vector xyz. So x1 is the first eigenvector corresponding to lambda equal to 2. So what is A minus lambda I? Here, in place of lambda, we have to take 2 because we are taking lambda equal to 2. So you write 2 here. So we need to subtract 2 from the principal diagonal elements. It is 1, 1, 4. After subtracting 2 from diagonal elements, 0, 0, 6, 0, 0, 3 multiplied by x1 is xyz. Let us take it as xyz. So you will get 0, 0, 0 here because 0 is nothing but the 0 matrix here. 0 is nothing but 0 matrix here. So from this, we get the equations x plus y plus 4z equal to 0. How do you get these equations? First row and this column. So first row and this column multiply corresponding elements, you will get 1 into x plus 1 into y plus 4 into z. So this is one equation. So coming to the second equation, 0 into x plus 0 into y plus 6 into z. 6z equal to 0. Remaining two are zeros. The third one also the same thing. 3z equal to 0. Whether it is 6z0 or 3z0, we get z equal to 0 only. So once we get z equal to 0, you substitute this z equal to 0 in the first equation, you will get x plus y plus 0 equal to 0, or x equal to minus y. So therefore, we have got x equal to minus y and z equal to 0. So the first eigenvector is x equal to minus y, right? So I write first of all x, y, z, x, y, z. So what is x? It is minus y, z is 0. Now choose a value for y. Let us take it as simplest value 1, right? So in that case, it becomes minus 1, 1, 0. So minus 1, 1, 0 is the eigenvector corresponding to the eigenvalue lambda equal to 2. Now coming to the eigenvector corresponding to lambda equal to 3. So what you have to do is a minus 3i into x2 equal to 0. So here, what is a minus 3i? It is subtract 3 from the principal diagonal elements in this matrix. So you put lambda equal to 3 here. 3 minus 3, 0. 0, 1, 4. 0, 1, 4. Coming to the second row, it is, we are taking lambda equal to 3, right? So 0, minus 1, 6. 0, minus 1, 6. Coming to the third row, 0, 0, 5 minus 3 is 2. 0, 0, 2. 0, 0, 2. Into xyz multiplied by xyz equal to 0, 0, 0. So if you take the product, what you will get? 0 into x plus 1 into y plus 4 into z. So y plus 4z equal to 0. Coming to the second column, second row, minus y plus 6z equal to 0. Third one, 2z equal to 0, because we have two zeros here. 0 into x plus 0 into y plus 2z. When 2z is 0, z becomes 0. When you put z equal to 0 in this, either of the equations, you will get y equal to 0. So therefore, we got y equal to 0 and z equal to 0. But what about x? Here you see all all the elements in the first column are zeros. So we have got 0 into x plus the second equation also 0 into x plus 0 into x plus, right? That means you can take any value for x, right? So whatever the value of x, it is going to satisfy, because it is 0 into any value is 0 only. Therefore, you can take any value in place of x. So therefore, we choose x equal to 1. But you should not choose x equal to 0, right? For x equal to 0 also, 0 into 0 equal to 0 only. But if you take x equal to 0, what happens? Already y and z are zeros. If you take x equal to 0, then these three equations may satisfy, but 0 vector cannot be an eigenvector. Therefore, you should select or choose some value of x other than 0 only. So therefore, you take x equal to 1, then the equation, the eigenvector you are going to get is xyz, which is, the second eigenvector is 1, 0, 0. In fact, you can take any value in place of x other than 1 also, right? That is also an eigenvector. Whatever value you take in place of x, you will get a eigenvector in the same family, right? But you should not take 0. Now coming to the third eigenvector. What is the third eigenvalue? Eigenvalue is 5. Therefore, a minus 5i into x3 equal to 0. So what is a minus 5i? So in place of lambda, you put lambda equal to 5. 3 minus 5 minus 2. Therefore, first y is minus 2, 1, 4. Minus 2, 1, 4. Coming to the second row, put lambda equal to 5. 0 minus 3, 6. 0 minus 3, 6. Coming to the third row, it is 0, 0, 0. Because lambda equal to 5, it is 0, 0, 0. 0, 0, 0 multiplied by xyz equal to 0, 0, 0. So what are the equations we got here? Minus 2x plus y plus 4z equal to 0, minus 3y plus 6z equal to 0. So from the second equation, what we have got is minus 3y equal to minus 6z, minus minus 1, 3 here 2 times. Therefore, y equal to 2z. So y equal to 2z is one relation we have got. Now, you put y equal to 2z in this first equation. What you will get? 2x plus 2z. In place of y, you write 2z plus 4z equal to 0. So minus 2x plus 6z equal to 0. Minus 2x equal to minus 6z. Minus minus gone. Here 3 times. It is x equal to 3z. So the other relation is x equal to 3z. So y equal to 2z and x equal to 3z are the two relations we have got here. Now if you take choose z equal to 1, because if you choose z equal to 1, you will get x equal to 1 and y equal to 2. Right? You can also choose x equal to 1, but in that case z becomes 1 by 3. Right? 1 over 3. So this is better than that. So I choose z equal to 1. This implies what happens? X becomes 3, y becomes 2. Put z equal to 1 here. So therefore, x3 is xyz, and what is x? X is 3, y is 2, z is 1. We have chosen z as 1. So therefore, the eigenvectors are minus 1, 1, 0, 1, 0, 0, and 3, 2, 1, corresponding to 2, 3, 5. Eigenvalues 2, 3, 5 respectively. Okay. So here in this problem, we have got all three eigenvalues different and all three eigenvectors exist. Right. So in the next problem, we will see a different case, different scenario. Now let us take A equal to the matrix 0, 1, 1, 1, 0, 1, 1, 1, 0. So if you take this matrix, let us find the characteristic equation, because it is not a diagonal matrix or rectangular triangular matrix. Therefore, need to find the characteristic equation here. So how do you find the characteristic equation? It is lambda cube. We have discussed this in a particular video. You can go and refer that video if you want to find, if you want to know how to find the characteristic equation in short. Okay. So here also we are going to demonstrate the same. Lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. So here, what is s1? Here, s1 is trace of a. Trace of a is 0, sum of the diagonal elements, principal diagonal elements. What is s2? s2 is sum of the three determinants corresponding to the a11, a22, a33, cofactor matrices, determinants of. So therefore it is, you take 0, 1, 1, 0. 0, 1, 1, 0 plus all corners 0, 1, 1, 0, again 0, 1, 1, 0 plus top left corner 0, 1, 1, 0, 0, 1, 1, 0. So it is minus 1, minus 1, minus 1, minus 3. So negative 3. So and S3, what is S3? S3 is determinant of A. What is determinant of A? It is 0 into, anything is 0, minus 1 into, leaving this row and this column, you will get 0 minus 1 minus 1 plus 1 into, leaving this column and this row, you will get 1 into 0, 1 into 1, 1 minus 0, 1. So it is 1 plus 1, 2. So therefore, the characteristic equation is lambda cube minus S1 lambda square plus S2, but S2 is negative here, therefore minus 3 lambda minus S3, S3 is 2. So if you use scientific calci, you will get the eigenvalues as 2 minus 1 minus 1. 2 minus 1 minus 1 are the eigenvalues of this given matrix. Now let us find the eigenvectors of the matrix. So what is A minus lambda I here? Simply subtract lambda from the diagonal. It is minus lambda 1 1, 1 minus lambda 1, 1 1 minus lambda. So this is A minus lambda I matrix. Now, so what are the eigenvalues? The eigenvalues are 2 minus 1 minus 1. For the first eigenvalue lambda equal to 2, the equation is A minus lambda I into x equal to 0. Of course, x1. So what is lambda here? Lambda is 2. You substitute lambda equal to 2 in this place. So what you will get? You put lambda equal to 2 here. Minus 2, 1, 1. 1 minus 2, 1. 1, 1 minus 2. So minus 2, 1, 1. 1 minus 2, 1. 1, 1 minus 2 is the matrix A minus lambda I for lambda equal to 2. Here it is x, y, z, 0, 0, 0. So what are the equations we have got here? Minus 2x plus y plus z equal to 0. X minus 2y plus z equal to 0. X plus y minus 2z equal to 0. So if you take the last two equations, you subtract, what you will get? X gets cancelled. You will get minus 3y plus 3z equal to 0. So minus 3y equal to minus 3z. From this, we will get y equal to z. So y equal to z is one relation. You put y equal to z in the first equation, what you will get? Minus 2x plus z plus z equal to 0. So minus 2x equal to minus 2z. Again, we are getting x equal to z. So y equal to z and x equal to z. The two variables x and y are depending on one variable z. Therefore, if you choose z equal to 1, so what you will get? X equal to 1 and y equal to 1. So therefore, the eigenvector x1 is 1, 1, 1. So 1, 1, 1 is the eigenvector corresponding to lambda equal to 2. Next. Now let us find the eigenvector corresponding to lambda equal to minus 1. So here, minus 1 is the second eigenvalue. So for lambda equal to minus 1, it is A minus lambda I into x equal to 0. You put minus 1 in place of lambda in the matrix A minus lambda I. So if you put minus 1 in place of lambda, what you will get? 1, 1, 1, 1, 1, 1, 1, 1, 1. Right? So therefore it is 1, 1, 1, 1, 1, 1, 1, 1, 1 is multiplied by xyz is equal to 0, 0, 0. Here all three equations are same. Therefore, you will get only one equation, x plus y plus z equal to 0. So we have got only one equation where one variable can be written as function of other two variables. That means one variable is depending on the other two variables. One variable is depending on two variables. Therefore, we choose different values for yz, you will get a value for x. Right? So choose y equal to 1 and z equal to 0 here. What you will get? In that case, you will get x equal to minus 1 minus 0 minus 1. So therefore, x2, the second eigenvector, becomes minus 1, 1, 0. If you choose y equal to 0 and z equal to 1, so you always solve this kind of problems in this way. Okay, when one variable is depending on the other two variables, you take this one as 1, this 0. Next time, this one 0 and this one 1. Second variable as 1. So here 0, 1, if you put, what you will get? X equal to again 0 minus 1 minus 1. So therefore, you will get another eigenvector, linearly independent eigenvector, minus 1, 0, 1. So these are the three eigenvectors. 1, 1, 1 is the first eigenvector corresponding to lambda equal to 2. And we have got two linearly independent eigenvectors corresponding to lambda equal to minus 1. So we have got all three eigenvectors here, linearly independent eigenvectors, even though we have only two different eigenvalues. That means one eigenvalue is repeated. Now let us solve a different case. A equal to, let us take the matrix, again find eigenvalues and eigenvectors. So if you see, the characteristic equation is lambda q minus s1 lambda square plus s2 lambda minus s3 equal to 0. So what is s1? S1 is trace of A. Trace of A is 3 plus 0 minus 1. Sum of the principal diagonal elements 2. What is S2? S2 is the sum of the determinants of the cofactor matrices. Cofactor matrix of 3 is these four elements 0, 1, 2 minus 1 plus all corner elements 3, 3, 1 minus 1 plus top left corner 3 minus 4, 1, 0. The first one, it is bottom right corner, all four corners, and then top left corner. So it is minus 2, minus 3, minus 3, minus 6. It is plus 4. It is minus 4. Therefore, S2 is minus 4. And what is S3? S3 is determinant of A. What is determinant of A? Determinant of A is 3 into minus 2 minus of minus 4, 4 into minus 1 minus 1 minus 2 plus 3 into 2 minus 0, 2. So if you simplify, you will get minus 8 here. S3, which is determinant of A. So if you substitute all these three here, you will get lambda cube minus S1 is 2, 2 lambda square plus S2 is minus 4. So you put minus 4 here, you will get minus 4 lambda, and S3 is minus 8. Therefore, you will get plus 8 here. S3 minus S3 is plus 8. So if you solve this using your scientific calc, you will get eigenvalues lambda equal to minus 2, 2 and 2. So here we have got one eigenvalue different and two eigenvalues as same. So what is the matrix A minus lambda I? The matrix A minus lambda I is simply subtracting lambda from the principal diagonal elements 3 minus 4 3, 1 0 minus lambda 1, 1 minus 2 minus 1 minus lambda. This is A minus lambda I. Now let us find the characteristic vector corresponding to lambda equal to minus 2. It is A minus lambda I multiplied by x1 equal to 0. What is A minus lambda I? You put lambda equal to minus 2 in this matrix. What you will get? 3 plus 2, 5. 5 minus 4, 3. 5 minus 4, 3. Next, put lambda equal to minus 2 in the second row. 1, 2, 1. 1, 2, 1. In the third row, it is what you will get? 1, 2, 1. 1, 2, 1 again. Into xyz equal to 0, 0, 0. Simply here, these last two rows are same. Therefore, you will get the same equation for the last two rows. Therefore, the equations are 5x minus 4y plus 3z equal to 0, x plus 2y plus 2z, sorry, x plus 2y plus z equal to 0. So if you multiply the second equation, first equation is 5x minus 4y plus 3z equal to 0. Multiply the second equation by 2 to get 4y here. You will get these two gets cancelled if you add. It is 7x plus 5z equal to 0. 7x equal to minus 5z. So x equal to minus 5z by 7. So if you put x equal to minus 5z by 7 in the either of these equations, I take the second one, minus 5z by 7 plus 2y plus z equal to 0. It is 2y plus 2z by 7 equal to 0, or 2y equal to minus 2z by 7. 2 gets cancelled. You will get 7y equal to minus z. So we have got two different equations or relations, x equal to minus 5z by 7 and 7y equal to minus z. So you take or you choose y equal to 1. Right? When you take y equal to 1, what happens? Z equal to, this implies z equal to minus 7. So z becomes minus 7, and you put minus 7 in this equation relation, you will get minus 5 by 7 into minus 7. So it is 5. So therefore, the eigenvector corresponding to lambda equal to minus 2 is x is 5, y is 1, z is minus 7. So 5, 1, minus 7 is the eigenvector corresponding to lambda equal to 2. Now, what is the other eigenvalue? The other eigenvalue is 2 here. Now coming to the eigenvector corresponding to lambda equal to 2. So what we have to do is, a minus 2i multiplied by x equal to 0. So what is the matrix A minus lambda I? This is A minus lambda I. You put lambda equal to 2. What you will get? 1 minus 4, 3. 1 minus 4, 3. 1 minus 2, 1. And 1 to minus 3 you will get. If you put lambda equal to 2. It into xyz equal to 0, 0, 0. So what are the equations? X minus 4y plus 3z equal to 0. X minus 2y plus z equal to 0. The third one is x plus 2y minus 3z equal to 0. So if you add these two, last two equations, what you will get? 2z, 2z, 2y, 2y gets cancelled. 2x minus 2z equal to 0. This implies x equal to z. Now if you put x equal to z in the first equation, what you will get? Z minus 4y plus 3z equal to 0 minus 4y plus 4z equal to 0. So minus 4y equal to minus 4z, y equal to z. So therefore we have got x equal to z and y equal to z. See here, two variables are depending on one variable. So we have a chance of choosing only one value, right? If you choose one variable z equal to 1, you will obtain the values of two variables x equal to 1 and y equal to 1, because x equal to z, y equal to z. So therefore, we have got the second eigenvector as 1, 1, 1. And there is no possibility, because the third eigenvalue is also same 2. You will get this same eigenvector again, right? So here, this is an example of the problem where you cannot find the third linearly independent eigenvector, right? So third linearly independent eigenvector is not possible here, not possible in this case. So this is such an example, right? Because we are going to choose only one value, we are going to obtain the values of two variables, you will get only one vector. You can't find the third one. But if you observe in this problem, the previous problem we have discussed, here we have got one variable depending on two variables. X is depending on two variables y and z. So you have a chance of choosing two variables. So we have obtained the values of x in two different cases. We obtained two different eigenvectors, linearly independent eigenvectors. But in the present problem here, the two variables are depending on only one variable, right? X and y are depending on z. Therefore, we have a chance of choosing only one variable. In that case, you will get only one linearly independent eigenvector for lambda equal to 2. The other linearly independent eigenvector you cannot find in this case. So, for this problem, only two eigenvectors exist. The third eigenvector does not exist in this particular problem. Now we are going to see a different one, the fourth problem. Let us take the matrix find eigenvalues and eigenvectors. So here, if you find the eigen characteristic equation, it is s1 lambda square minus plus s2 lambda minus s3 equal to 0. So we have just explained in the previous problems how to find the characteristic equation, right? S1, S2, S3. S1 is trace of A, the given matrix A, it is minus 3 here. S2 if you find, you will get 3, and S3 you will get -1. So therefore the characteristic equation becomes lambda cube plus 3 lambda square plus 3 lambda plus 1 equal to 0, which is the formula of lambda plus 1 whole cube, right? So therefore you will get eigenvalues -1, -1, -1. All three eigenvalues are equal here. So this is such a case, right? So here, what is the matrix A minus lambda I? Write the matrix A minus lambda I. It is 6 minus lambda minus 6, 5, 14 minus 13 minus lambda, 10, 7 minus 6, 4 minus lambda. This is A minus lambda matrix. A minus lambda I. The eigenvectors corresponding to the eigenvalue -1. You have only one eigenvalue here. So what is A minus lambda I into x equal to 0? It is, you put lambda equal to -1, you will get A plus I into x equal to 0. Simply you substitute lambda equal to -1 in this matrix. What you will get is 7 minus 6, 5, 14 minus 14, 10, 7 minus 6, 5. Acting on xyz equal to 0, 0, 0. So if you carefully observe, the equations are all same. 7x minus 6y plus 5z equal to 0. The second equation is also same. By cancelling out 2, you will get the same. Third is also same. So you have only one equation in your hand. So from this you can write 7x equal to 6y minus 5z. Now this is the relation between x, y, z. So what is the vector x? It is x, y, z. X is, from this you can write x as 6 by 7 y minus 5 by 7 z. So 6 by 7 y minus 5 by 7 z y z. So I have written this one in place of x, y and z as it is. Now we have a chance of selecting two variables, right? So choose y equal to 1 and z equal to 0. You will get one eigenvector as 6 by 7, 1, 0. You multiply the entire vector by 7, you will get 6, 7, 0. You can also do like this. Next, you choose y equal to 0 and z equal to 1. You will get another eigenvector, linearly independent eigenvector. It is y0 z1 means minus 5 by 7, 0, 1. You multiply the entire vector by 7, you will get minus 5, 0, 7. So we have got two eigenvectors, linearly independent eigenvectors for lambda equal to -1. Then what about the third one? You cannot find the third eigenvector. Therefore, only two possible eigenvectors. Two eigenvectors only possible. So there is no possibility for third eigenvector in this case also. Okay. So here this problem is an example of all three eigenvalues are same, but we have got only two eigenvectors. Third eigenvector does not exist. Next, coming to another type of problem. So if you take this matrix, what you will get is the characteristic equation. If you find, it is S1 equal to 3, S2 is 3, S3 is 1. So we will get the characteristic equation as lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. And this is simply lambda minus 1 whole cube equal to 0. Lambda minus 1 whole cube equal to 0, which is lambda equal to 1, 1, 1. See, here also all three eigenvalues are different, same. All three eigenvalues are same like in the previous problem. In the previous problem, it is all three eigenvalues are same but minus 1. Here it is 1. So let us find the eigenvector corresponding to lambda equal to 1. It is a minus lambda I into x equal to 0. So what is a minus lambda I? Subtract lambda from the diagonal, principal diagonal. It is here lambda equal to 1. Therefore, subtract 1 from the principal diagonal. 0 minus 1 minus 1, 1, 0, 0, 0 minus 1 minus 1, 1, 1 minus 3. Here 3 minus 1 is 2. X, Y, Z. So what I did here is simply I subtracted lambda equal to 1 from the principal diagonal elements. And the remaining elements are same. 0 minus 1, 0 minus 1 and 3 minus 1. So we have got the equations minus x plus y equal to 0, minus y plus z equal to 0. From the first one, we got x equal to y. From this equation, we have got y equal to z. So if you choose z equal to 1, what happens? We'll get y equal to 1 and x equal to 1. So therefore, we have chosen only one value z. We have got two values for x and y. Therefore, the eigenvector is xyz, which is xxx 1, 1, 1. So this is the eigenvector we have got here for lambda equal to 1. But what about the remaining two eigenvectors? It is not possible here, right? So we have got only these relations and we got one eigenvector. Because the two remaining eigenvalues are also same, you will be getting the same equations again and again, and you will be getting the same eigenvector again and again. So therefore, only one eigenvector. Three eigenvalues are same, but only one eigenvector is possible in this case. In this case, okay. Now, so this is a typical problem, somewhat different problem. We have to go through it. Then only we will understand. So if you find the characteristic equation, you will get lambda cube minus 6 lambda square plus 11 lambda minus 6 equal to 0. I am directly writing it. Okay, S1 is 6, S2 is minus 11 and S3 is delta A, which is 6. So if you find the eigenvalues using calc, you will get 1, 2, 3 as eigenvalues. For lambda equal to 1, first eigenvalue, the equation is a minus lambda I into x equal to 0. You put lambda equal to 1 in this. That means subtract lambda from the principal diagonal. You will get 1, 0, 1, 0, 1, 0, 0, sorry, 1, 0, 1, 1, 0, 1 again. That means we have subtracted 1 from the principal diagonal into xyz equal to 0, 0, 0. So we have got the equations x into 1 plus 0 plus y into z into 1. So it is x plus z equal to 0. From the second row, we have got 0 into x plus 1 into y plus 0 into z. So it is 0 into x plus 1 into y plus 0 into z equal to 0 implies y equal to 0. So one parameter is fixed, y equal to 0. And from this equation, we have got x equal to minus z. So therefore, the eigenvector for lambda equal to 1 are x, y, z. You choose z equal to 1, choose z equal to 1, what you will get? X is minus z, so minus 1, y is 0, z is chosen as 1. So the first eigenvector is minus 1, 0, 1. Coming to the second eigenvector corresponding to lambda equal to 2, for lambda equal to 2, it is a minus 2y into x, x2 equal to 0, second eigenvector. You subtract 2 from the diagonal, it is all zeros, because all diagonal elements are 2's, you will get 0 in the diagonal. 0, 1, 1, 0, 0, 0, 1, 0, 0. Multiplied by x, y, z equal to 0, 0, 0. So this is a typical one. You see, from the first one we have 0 into x plus 0 into y plus 1 into z equal to 0. That means z equal to 0. From the second row, it is all zeros. From the third one, it is 1 into x plus 0 into y plus 0 into z. So x equal to 0. So two variables are fixed to be x equal to 0 and z equal to 0. Right? Then what about the third one? Because in the second equation, 0 into x plus 0 into y plus 0 into z equal to 0. Right? Corresponding to this row, you will get this equation. Here x is fixed to be 0, y is fixed to be 0. So you have only 0 into y equal to 0. So x is 0, z is 0. Then what about the value of y? So you have a possibility of choosing the value, choosing the value of y. It is in your hands to choose the value of y. So you can choose any value for y, but you cannot choose 0 in place of y, because if you choose y equal to 0, you will get a 0 vector here, which cannot be an eigenvector. 0 vector cannot be an eigenvector. Therefore, you have to choose a non-zero value for y. Still, it satisfies 0 into y equal to 0. So I choose 1. So therefore, the second eigenvector is x2 equal to 0, 1, 0. So coming to the third eigenvector corresponding to lambda equal to 3, it is a minus 3i into x3 equal to 0. So subtract 3 from the diagonal, what you will get? 2 minus 3, minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1. Because all diagonal entries are 2, 2, 2. When you subtract 3, you will get minus 1, minus 1, minus 1. So what are the equations? Minus x plus z equal to 0 implies x equal to z. From the second one, it is minus y equal to 0. Minus 1 into y equal to 0, which is y equal to 0, which results in y equal to 0. So third row again, you will get x plus x minus z equal to 0 is same as the first equation, x equal to z. So you have got x equal to z and y equal to 0. Therefore, if you choose z equal to 1, what you will get? X equal to 1, y is already 0, z equal to 1. Right? So this becomes the third eigenvector corresponding to lambda equal to 3. So first eigenvector is minus 1, 0, 1. Second eigenvector is 0, 1, 0. Third vector is 1, 0, 1. So this is a typical problem, right? So we have discussed all 6 different types of problems, possible different possible problems in the eigenvalues and eigenvectors. Now we can do or solve any problem based on eigenvalues and eigenvectors. Thank you so much. Please subscribe to my channel if you have not subscribed it. Also like the video, share it with your friends and classmates. Comment your feedback, and if you require any other topics, let me know. I will discuss here. Okay. Thank you.